Okay, welcome everybody. I would like to open this session about advanced IP and optical networking. I think in the beginning yesterday somebody said that bandwidth should be free, so that everybody can use it up to the most. So let's see how we are going to implement that. There are three people who are going to say something about that technology, how to combine the IP technology together with the optical. And of course, that's important to combine them because IP is still available protocol. I think most applications will still utilize that. And how do you integrate then the optical in that environment? First of all, Monique Morrow from Cisco will talk about these wavelength switching technology, what the time frames are, what kind of possibilities there are, and how it fits these two together. So I would like to give Monique the floor, and so that she can say something about her thoughts, how to do that in the near future.
Thank you. Good morning, everyone. My name is Monique Morrow, and actually I'm going to talk about the advanced optical technologies and the potential timeframes, which is actually, one could say, a continuation of Ed Seidel's plenary session yesterday, and a continuation of what is to follow today, and in this particular session with my colleagues. Now, this is in consortium with my colleagues Grasa Calvario and Peter Tomsu, and I'm actually in a grid middleware session this afternoon as a follow-up. So what the philosophy here is to give some highlights perhaps, or some trends perhaps, as to where the technology is going, what could be abstracted as readiness, what needs to be done, for example, in terms of standardization, what's happening in terms of actual requirements and applications, which we're going to hear quite a few information about in the next few days. So requirements from an advanced photonic infrastructure perspective, as well as looking at switching technology and transport format, switching nodes and control and signaling. What kinds of control and signaling behavior are we looking towards as we extend possibilities for lambda grids, and as well as the optical grid transport, and some conclusions and observations that will follow from my perspective. What I will talk about is by no means exhaustive. By no means exhaustive, so bear in mind that these are sort of, again, a roadmap, if you will, a map in terms of highlighting what we see and observe in the industry. So again, we look at some application examples like high energy particle physics. We're seeing, for example, data reduction systems where you have outputs between 10 and 100 terabit data sets, and really looking perhaps at possibilities of tens of petabytes in around 2008, and perhaps an exabyte to 2015. So very much the trend is in terms of being able to have bandwidth centricity capabilities in the network. We look at, for example, the optical networking internet protocol computer work that's being done. You have really the construct that a central architectural element is optical networking. And it's not really, as we're hearing, and we will hear before, a construct of computers, but rather super networks. The networks become really those computing elements, if you will. So the shift really is towards applications-driven types of constructs, and where we really have to have an assumption here is the existence, if you will, of some sort of lambda grid world. So again, when we look at this, we're absolutely abstracting requirements in terms of being able to have the generation and support of terabytes and petabytes eventually, and into the exabyte mode. Well, Larry Smarr has been quoted, and was quoted yesterday, and has been quoted and will be quoted, I can imagine, throughout this conference. But basically, fundamentally, quotes around what we need in terms and require in terms of computing needs around 2010. It is really the decade of grid, really end of the decade of grid-intensive applications, and we fundamentally, to quote him, is quote, will require an international distributed cyber infrastructure based on petascale computing, exabyte storage, and terabit networks. So we're looking at tremendous amount of capacity and capability where really the network becomes that which is going to be a determinator or an intelligence aspect of, for example, of those applications. So what does that mean? That means that we change from a processor-centric to a bandwidth-dominating computer paradigm. And so this is something that we need to think about as we move forward. And it's an opportunity in the industry to look at how we shift from that computing centricity to actually a network of super networks. So what does that mean when we look at optical switching technology possibilities and those transport format considerations? One transport format could be, for example, where one manipulates bandwidth through optical switching based on, for example, a wavelength level, which is functionally circuit switched, or we can take it at a very discrete level where we have, for example, a sub-wavelength level where you have optical burst and optical packing switching functionalities. So here you get into a little more granular attributes, if you will, in terms of switching in optical format constructs. Then we look at the opportunity to have a wavelength switching or photonic and lambda switching, where we switch, for example, have the capability to switch wavelengths on separate paths, or you have DWDM enablement of virtual paths like light paths. Then there is the mode that we see also discussed in the industry, a hybrid router wavelength switching construct. So you have IP-aware clients which will interface between applications and the lambda switch network. Now, if I take and develop the optical technologies further, one transport format example or sets of examples include OBS or optical burst switching, where one could transmit burst mode via an optical and assume no bufferless network. So we have a bufferless network. And then we have also flow switching or perhaps what could be perhaps switching capabilities, i.e. allowing, for example, a single burst capability. Then we get into switching timescales from micro to milliseconds. So we absolutely get into some interesting timescale opportunities there. Another example for what we see also is optical flow switching, whereupon we will have a switched entity in terms of sets of consecutive packets capabilities. And here we have the attribute of a header that would be attributed to or attached to a flow, which would be, for example, have the behavior of a single packet. Again, it's hop by hop, and here you get into nanosecond scale capabilities up to 10 to 40 gig. And the third example would be in optical packet switching function or capability. Again, you could have this header attached to the payload and would absolutely have a hop-by-hop path setup, providing where we have buffering requirements, where we would have a constraint here with this particular function of optical memory capability. We see the capacity or functions to permit, for example, packet lengths from 50 to 30,000 bytes. Proceeding, there is the concept of wavelength switching, and I will have some colleagues who will follow me who will talk a bit about wavelength switching. If we look at from an application aware, what we see, while we're talking about infrastructure and technologies, we cannot forget what really drives this. And what really drives this is the application awareness. So you have, for example, the network infrastructure would consist of optical switches, and you would have an integrated add-drop multiplexer or an optical multiplexer functionality, where the bandwidth granularity would be in the range of OC48 and OC768. So here, the control plane assumptions would be GMPLS. And GMPLS being able to do, perform such capabilities and functions as sub-second setup times using, or perhaps RSVPTE or CRLDP types of signaling. Perhaps having also the construct of optical VPNs to be able to share that capacity. So optical VPNs become an interesting service, if you will, or from a let's say a user perspective, and an optical uni for interdomain connectivity. Now, you have strengths and issues, or what we call pros and cons, or what we call let's say factors in terms of discussions in each of these modes. So from a hardware infrastructure, one of the strengths could be, well, you have existing hardware. Maybe this is something that one has in their infrastructure network capability today. There is work ongoing or currently doing this type of, providing these types of functions. And there is also the taking it from an optical VPN to have what we would call short-lived grid relationships. Challenges or issues that we need to think about moving forward is, for small data transfers, this may not be interesting. Probably more interesting for actually bursting, actually prolonged data transfers. And, well, not really very applicable or interesting for interactive constructs. So vendors will have to, it is expected, of course, vendors would have to make or look at extending extensions to their control plane behavior. And it is also assumed, or one could assume, that there would be the capability of offering optical VPNs, which is highly in a discussion mode, or looking at a discussion mode today in terms of what would that mean for from a carrier's perspective. And from a carrier perspective, then you get into what I would call beyond layer 7, which is layer 8 and 9 and 10. How do I make money from this? This is also a very major discussion. So wavelength switching from a software perspective, we get into really capabilities that we have to look at in terms of developing or requirements, if you will, i.e. scheduling or scheduling mechanisms for these wavelength services. You can have, is it going to be a traditional on-demand scheduling construct? Is it going to be future scheduling? Is it going to be one that I could just schedule when I want to? There are job scheduler types of capabilities when we look at the Grid Resource Allocation Manager, GRAM. So grid, where you have a grid network allocation that could function, that could potentially be based on a diffserv, differentiated services construct. Or the requirement, for example, to be able to support these particular resources. There is just quite a bit of discussions. What kind of, the open grid interface, looking at resource specification language, whether we have it, which is XML based, and then being able to present wavelength resources to our clients. There's also, for example, the general purpose architecture for resource and allocation. And what we get into when we talk about really what's the heart of this too, is not only having the super network and networks, or extending what I would call optical super worlds here, or grids, grid capability, but also we get into really the issue of resource allocation, reservation and resource allocation. So here we talk about bandwidth broker. And I'm often asked, and the industry is often asked, is there anywhere in the industry that is actually standardizing on a bandwidth broker function? The closest that you can get, perhaps from an IP perspective, is IETF, perhaps Path Computation Element Working Group. But that's the closest. So it is a call, perhaps, to be able to look at, bandwidth reservation and bandwidth broker means different things to different people. So we really have to think about what it means to provide standardization in that area. There's also the hybrid router wavelength switching mode and capability that we are seeing in the industry. And here you have where you extend the switching to an architecture by IP routers. So you have IP routers in the infrastructure. And these routers would, in terms of function, be able to provide full line rate switching, packet switching. They have router-to-router connectivity from a uni perspective with some extensions. And you would have the control, visibility, if you will, of a grid connectivity API. The control plane functionally is really assumed here to be GMPLS. And some of the strengths and issues, again, for discussion, or it has, one could say, you have IP packet networking with optical capability, interfacing to, for example, what Olivier will be talking about is optical switching or wavelength switching. Again, it's here. It's something that exists today. So, but what we need to look about is not, and to study further, and to really develop that which is what the call to industry is asking for, which is really the grid application awareness capability. So here it's looking at some of the resource requirements from a wavelength perspective, what needs to be defined, yet to be defined from a grid to application awareness when we do something like that. And, oh, by the way, we have to bear in mind of what we're doing to manage this. What about OAM? And OAM, while we talk about capacities and capabilities and an awareness in terms of what we want to do from an end user perspective, who manages it is something we need to think about in the end. Or how does that get managed? Then we have optical burst switching, which really is very nice complementary of optics and electronic strengths here. So here you have really the concept of a control message that would be set to an optical switch at the Ingres switch, and then you would have the forwarding messages along the data transmission path between those particular switches and nodes. So the process, so you can see sort of a hop by hop type of paradigm when we look at what actually transpires in terms of OBS functionality. The data plane is actually, the data plane function is assumed, for example, to be launched at what we would call an offset delay. So bursts would remain only, this is really the assumption in terms of capabilities, in the optical domain and end-to-end, and I put end-to-end in quotes. So whereupon we would assume a burst as in a contiguous form of data bytes or packets, and then the encoding or completely, function of encoding are completely transparent to those optical switches. So here you have what we would call high bandwidth, so deterministic, or rather deterministic transport construct, again with what we would call low latency capability, and with the function or what would be in terms of the service offered to the end user and all optical data transmission path for that particular application. So, but what kinds of enhancement would we expect to see for OBS in terms of OBS constructs? What we need to look at is it's still in the pre-standardization phase. So that's one thing. It's still in the pre-standardization phase. So we, as an industry and as a body, as yourselves, have an opportunity to drive that. Also, there is the look, we have to see, for example, about high demand of those applications for new transport protocols, what that means. What are the attributes that we must have, i.e. no buffering? Or what kinds of error rates, if any error rates? And then we look at what forwarding and routing algorithms that must be sort of developed here based on, for example, how on the optical plane, on forwarding plane decisions that need to be actually developed, and using, once again, GMPLS as a control plane to do that. If we look at e-science and grid application constraints, we have the assumption that we need to have a deterministic quaz model. We have to have real-time multicasting. And again, looking at what kind of control or who controls the lambdas. And how is that control given? This gets us into sort of a user control light path construct or capabilities, if we think about that, in existing, not competing against, for example, a GMPLS or whatever. If you are offering a service, how do you bill for that service? Or what should be done for billing? Now, I'm in the ITF and I'm in the ITU, and they're talking about one of the most contentious things and topics is billing and settlements, and how do you do that? And if we're looking at grid SLAs, what kind of network provides it? So moving forward, we have optical switching nodes, and again, these are sort of the functions from an input switch matrix output function, looking at signaling conditioning and wave bands and wavelengths and bursts of packets. Photonic switching in itself, or cluster interconnects. I talked about multicasting, but this could be an entire workshop on multicasting, on optical multicasting. But what we see are 2 to 5 years out. Optical connections will move between circuit boards inside the computers, and about 5 to 10 years you'll see chip-to-chip or chip-to-chip actual optical connections that will ultimately emerge in terms of what we see in terms of trends. So we have grid computing clusters using optical interfaces today, application level programmability of photonic switches, and then getting into what we would call different virtualization pattern with photonic multicasting capabilities. And photonic multicasting, as I said before, is quite an interesting subject. And then what we would need to consider would be routing and wavelength assignment in terms of looking at what kind of lambda optic trees and lambda paths that we need to consider in terms of what functions and algorithms have to be developed. Control, separation and control in data plane is still required or assumed, where we have control to actually refer to the infrastructure and intelligence capabilities, the discovery mechanisms, and being able to have algorithms that will provide the end-to-end quaz capability. We also see intelligent network elements that will perform or do perform circuit provisioning and failure recovery. So some of the standardization bodies talking about the control plane and the control plane functions include the ones that I have up here. But there are vendor proprietary implementations today, and that's primarily because it's time to market consideration. So the question we need to ask ourselves as a body is, how far does a grid transport control plane need to be standardized? Because you're going to talk about grid transport planes and grid control planes. We'll see that as a discussion at the GGF meeting in Chicago at the end of in June. At the end of June, we get into grid resource network interfacing again for dynamically entering and leaving for agreements that are application aware. A grid uni model to look at job submission, job reservation, and execution of those applications. So very, very interesting work that is being developed and looked at as we speak. Optical networking architecture, as I start to go for my conclusion. Quaz, virtual operators. We have a number of interesting dynamics that we see. What are small participating locations or ad hoc virtual operators for what is can be highly unpredictable, small, unpredictable, large, what I would call optical islands in the end, and the requirement to have what we see is an ad hoc model that's being more and more favored by that grid community, and the trend towards a peer model. It used to be, when we talked to a lot of carriers or traditional carriers, it was more, I want to deal with the overlay. But peer is coming up as a very, very interesting topic, and looking at peer model for the implementation of optical VPNs eventually. So let's not forget security. Let's not forget those OAM and trust model factors that need to also be considered when we're looking at this. Some conclusions. So we do see underlying transport networks can use some of what we would call standards or emerging standards, types of control plane capability, i.e. GMPLS. It's still far from being complete. It's evolving. There are pieces that are being developed, like interdomain, or being discussed for deployment expertise. Other areas that we have an opportunity to look at and develop and have a very, very major discussion on are the bandwidth broker integration. I talked about what is bandwidth broker, completion of the AAA for security, and the virtualization of services or network infrastructure. From a vendor perspective, there's always this give us your feedback. Talking about a long-term strategy and sharing the experience. And we have many, many, many early adopters who are willing to drive that and drive the pre-standards to standards and drive these capabilities as we speak in the industry today. Thank you very much.
Thank you, Monique, for the very interesting and challenging ideas. I think there are lots of issues we still can work on, which is nice, at least for our community, but there are some solutions, I think. That's good to see that. Other questions? I have time for a few questions.
Questions or comments?
Yeah.
What's your observation?
Perhaps I have one myself. I have several, but I'll start with one. Bandwidth broker, I think, is one of the areas you say we need to work on. Sometimes I look in history, and bandwidth brokering was very important when looking at DiffServ and so on. That stopped in some way. Do you think that we advanced, and what are the advantages from, let's say, what we did a few years ago? Are we able to do it now?
I think what we see, well, again, it goes down to what is bandwidth broker. We see sort of the control plane implementation of. You see, there is a community of folks who believe, okay, this function could be primarily developed out of control plane. However, what we are seeing now is more of a resurrection of bandwidth broker as a topic, especially in these types of services, and I think, in my opinion, and what I would predict is that this is going to be resurrected more. That you're going to see perhaps some attempts to really try to get a standardized bandwidth broker. I've been asked by several carriers, what group is standardizing on a bandwidth broker? What is the common definition of that in the industry today?
So that's important to get the standard over there. So, okay, good to know that. More questions that's popped up? No. Then I want to thank you again for your good thoughts. And I want to introduce the next person who's going to enlighten us about the optical lambda switching. That's Olivier Girafagnon from Calient. I think it fits nice in what we heard before. And one of the things, at least he's going to, at least that's in his summary, is talking about cost and performance. I said we have to give these networks for free to our users. So it's interesting to know what the costs are, and at least to have an idea about that. And I think that the idea of the automation using the control plane is a good idea to see how that is going to be implemented in these future optical networks. So I would like to give Olivier the floor as soon as his audio is working. And I think there he is. I have to get the other slides on. Now I can check my Polish. How do I get the next slides? My Polish is not so good. Sorry about that. Oh, there are short keys which are always the same. Of course, that's standardized. But yeah, that's correct. Yeah.
Thank you.
Okay, thanks, Olivier.
Good morning. It's a pleasure to be here today. My name is Olivier Jaffagnon. I work for a company called Calais Networks in California, but I'm actually French, and I worked in Europe before that in various industries. And actually, I was part of the European Molecular Biology Lab when I started in the mid-90s, and we were one of the first users of the for bioengineering projects of the European networks. The subject of my talk today is the impact of photonic switching technologies on the IP optical network architecture that you can use for advanced e-science applications. I will start first by giving you a state-of-the-art snapshot on what is the status of the technology and how it has impacted some of the first architectures that emerged. I will also, in the second section of the talk, go in more details about how you can use that architecture for these new e-science applications and grid applications. At the end, I will spend some time to go and look at very specific case studies. It's always interesting to look at what people have done in the past and learn from what they have done well, rather than just start fresh. And finally, as a conclusion, I look at what's next for the switching technology in that application environment. So what's new about switching? Optical switching has been used for a very long time, mostly 1x2s, 2x2s. It's a circuit switch technology that has been used in the phone industry for a long time. What's new is we have finally solved the scalability issue. We know now how to make very large switches. That's the big thing that's changed 2 or 3 years ago with 3D MEMS. You still have a large number of technologies that can scale in switching speed from millisecond to nanosecond, but they haven't solved the scalability issue at other speeds. So today, what's the status? Still, the majority of switches today are deployed for are 1x2s, 2x2s for simple protection application. But there's an increased deployment actually of large photonic switches. There are 320s by 320 switches in service today. So it's real. It's carrying live traffic and generating revenues. Just a quick side note. There's a difference between a bare switch matrix, like a non-redundant fiber switch matrix, like you can have an electrical switch fabric, and what I would call a cross-connect systems where you have full redundancy and modularity. In that case, it's very close to an OEO type of cross-connect, except the core matrix is all optical as well as the line cards. I think some of the things that were a worry for people in the industry 2 or 3 years ago is maturity and reliability. It's a much more mature technology today. Photonic switches are carrying live traffic for more than 3 years now. There's multiple vendors, with 3D MEMS technology being the main technology above 16 by 16 sizes. Also, on reliability standpoint, they're intrinsically much more reliable than OEO, simply because there's much fewer components. If you look in O, there's about 3 to 4 components, and OEO architecture is 20, 30 components for the same fit, because it's the same semiconductor technology. It means it's 10 times better, 10 times more reliable. There's still obviously ongoing research on fast switching, because it will still be needed in the future. However, scalability limitation again. And some people are looking at existing technologies. We have actually demonstrated sub-millisecond performance on 3D MEMS, and as well as a Japanese manufacturer. Application of that technology, mainly 2 aspects. Optical exchange points. If you look in its simplest form, you can look at a photonic switch as an automated patch panel. Simple as that. Instead of having operators making patches, you do that automatically. So you can use that to reconfigure interconnectivity, or to also share monitoring, so you can observe the network more cost effectively. Now, if you put that with a control plane in the core of the network, it becomes a more networking tool, much more powerful. I've seen 2 main applications, and from a topology is going to drive 2 different architectures. One is more in the original network environment, like states in the United States or some countries in Europe. It's still going to be mostly ring-based, so you're going to use that technology to interconnect rings. extend management across multiple rings. But you can also look at national backbone. In this case, it's a real mesh infrastructure. And you can use switches for other applications like transponder and fiber protection, again, automated capability, and also wavelength switching and services. Impact. There are really 4 impacts. The first one is cost. A 10 gig photonic switch port, although it doesn't do the same function, is 2 orders of magnitude less than IP. So when you're doing kind of static, large data transfer, it becomes very interesting to massage 10 gig connectivity with a photonic switch. It's 1 order of magnitude less than an SDH cross-connect. The other reason is scalability. You can, the cross-connects are much larger. So 320 at 10 gig is 3.2 terabit in a single stage. So it scales better. It's also lower footprint and lower power consumption. The other aspect is flexibility. You can remotely reconfigure your connectivity, and you can do that regardless of the format. You can also do a better use in a facility-based network, better use of the network resources. The other, I think, argument, which is very attractive for that community in particular, is it's future-proof. It's really transparent. So as people are going to look at 40 gig or other technologies, you're not going to have to change that infrastructure. So in summary, look at photonic switching at extending the value of dark fiber that people understand very well now for the physical connectivity to the layer 1 switching. That's what it gives you. It gives more control, more flexibility, and it empowers you. I'm going to look at, as the NREN example, it actually, when you look back it makes a lot of sense that some of the NRENs have used photonic switching for the network. So the reason behind that is there's been increased interest in higher bandwidth connectivity. When you go to higher bandwidth connectivity, you start to look at other technologies. There's been interest worldwide for that type of new applications, grid computing, big science. Something is very important. You're not the only ones to be interested in that. I'm always amazed. People think they're doing something different from anybody else. So I'm an engineer. The first thing I do when I look at a problem is look at what other people have done. Researchers might look at a new way of doing things, but government and military applications have networks doing exactly what you're doing for different purposes. And there are some carrier customers looking at something similar, like wavelength services for business continuance. So you're not the only ones to do that. The good news, you're not alone. So you can get some help. There are differences in service definition implementation, so that creates a lot of confusion. Level of control over this facility-based connectivity, what people call light paths, service requirements, and also access to fiber. What's common? There's access to some fiber in most cases. There's a need for a guaranteed bandwidth connectivity and a need for some control plane. So as a result of that, you've seen deployment of new type of networks, hybrid, IP and optical, and facility-based. It's a totally different way of running a network. It's not an overlay. You own the assets, and you have to do a lot more different things. So this is why, if you look at the impact of one technology among others, like photonic switching, this is why some NRENs were some of the first to use a technology to achieve these goals. So 2 examples, HEAnet in Japan in 2002, and Optical in 2003. So again, if you look at the reasoning behind it, it makes sense why they have decided to use that. I'm not going to spend too much time on this slide because I think people know that very well. But again, I think we're in a paradigm change in the way people build networks today that's very important. An example of hybrid architecture, if you put a photonic switch in the middle, there's 2 things that happens. You can do whatever you want on the transport options. On the transport side, you can choose, you can connect your release circuits that you already have or you have to buy because it makes more business sense. You can deploy DWDM or CWDM over fiber or 10 gig over fiber. It doesn't matter because you can manage that with a transparent switch. So it gives you a lot of options on the transport side. If you go purely SDH, then you have to do SDH. On the client side, it allows you to share that high capacity connectivity on the wide area side to many users. Usually in your community, you have much more users than capacity. So how do you share it? You also have more than one type of services. How do you share the connectivity among different services? Another thing that's very specific to your environment is you both have what people call production quality and experimental. Some people want to break the network, some people want to make it very stable. You cannot do that very easily in IP because it goes through the same electronics. But in a circuit switch environment, especially a photonic switch, there's a physical separation between connections. So you can break some while you can keep the other one stable much more easily than in IP. There's a need for control plane behind that. The first reason the first reason is when you go with an architecture where you use WDM over fibers and you plug clients, you have to provide some protection services. If you have unprotected services, then you have service agreements problems. So you need some capability to do protection. That's what a photonic switch can provide you. There's also an issue of interoperability across multiple vendors and layers. How do you make routers cooperate with switches, DWDM, and layer 2 switches? That needs to be addressed. And there's also this idea of end-to-end connectivity, how you go across multiple domains. For the three reasons, you need a control plane. Today, there's a lot of work, as Monique explained. There's still a lot more work to do to really deliver on the premise. I mean, there's been a lot of work, there's a lot of things there, but GMPLS and ASON, GMPLS being just the protocols, the tools, and ASON more the architecture, have to be further developed and standardized so people can build those networks. There's always the issue of multi-vendor interoperability. Standards is one thing, but implementation, sometimes there's a lot of details that need to be addressed. There needs to be coherence between standard bodies. ENNI is a very good example. There's an ENNI being defined OIF and ATF. They use 95% of the same protocols, but guess what? If you put them together, it's not going to work. There's some subtleties that don't make it work. That's going to be fixed at some point, but today it does not work. So be careful. User and network interfaces, obviously. So remember, GMPLS is a flexible and powerful set of tools that does signaling, routing, and link management, but it's not a magical thing that's going to do bandwidth on demand for you. That's not true. It does not provide, for example, functions like scheduling, authentication, reservation, authentication. So this needs to be addressed at service layer to really complement and provide you a bandwidth on demand service type of things. So you should see just as a foundation that you can leverage to do what you want to do. So one example that is, I think, very timely for your community is how you're going to provide a layer 1 type of service or an optical VPN or whatever you want to call it from a campus to another campus going through at least 2 NRENs and a pan-European backbone. That's not going to be trivial. You can do that in IP in layer 3 using IP protocols today, but in layer 1 there's going to be a lot of work to do that. But that's what the control plane can do for you. So I just talked about the fact that there's a work to do inter-domain across networks to provide a similar service at layer 1 than layer 3. So that's one strong area of work for the control plane standardization community. But I think your community has a lot of work to do what I call the vertical aspect, which is to integrate that control plane, or what we call control plane, because people might have a different idea what a control plane will be, with what I call more the service layer, the layer 4 and above. So for example, there have been some first experiments of integrating AAA and Mona Lisa or others over GMPLS to provide intelligent services. There's an importance of a model to define how people are going to interface control planes, capabilities, and some of the things that do not exist today, and the application that ultimately you want to run more automatically in a more pervasive way. And the challenge I have for you is you'll get a layer 1, layer 3 technologies being developed by the industry pretty well, and you should leverage that actually. But the grid, the adaptation, the reservation is something that commercial carriers, that the industry is not really going to do because it's never really been done before. And it's really your challenge to drive that, because we're not going to do it. So this is your challenge. I just put a few pictures of how it could be done, leveraging different technologies. Okay, now the last part of my talk, I'm going to take some very specific case studies. So real examples, I'm going to look at exchange points. I'm going to take the Optical case between Chicago and Amsterdam, ultralight, also in Los Angeles. Some core networking applications in Japan, HEAnet and JGen2, a regional network in Louisiana. Actually, Lonnie is a network that will support Ed Seidel's work that he spoke about in the keynote yesterday. So while I'm going through those slides, look at the various usage and applications. It can be automated configuration as a main reason to use that, to use photonic switching, intra or inter-domain switching routing. Look also at what applications are run over those networks and services are enabled. So in Optical case, what was very interesting is they decided to bypass router and SDH when and where it makes sense. For example, across the Atlantic, obviously you're not going to do that. But in some applications, they provided for high bandwidth customers, they provided direct connectivity. And they were able to provide much more capacity at guaranteed bandwidth at much lower cost. So that was very interesting. The other interesting they did is on a small network, obviously 2 nodes, they start to integrate AAA with the layer 1, and they start to play with brokered services. So that's the other, I think, big thing they did a couple of years ago. Now, the demonstration was done with a direct interface using TL1 between the AAA and the devices. That's not really scalable. As you're going to grow multiple domains, various components, you're going to really need a real optical control plane. Ultralight, it's similar, but a little bit more advanced. It's more recent. They use a switch as a flexible tool to interconnect various devices and various networks. They are developing dynamic services for high energy physics, so in parallel with the LHC program. So again, the first thing they did is they have some green middleware called Mona Lisa and some hardware. So the first thing they did, they interface it. Again, they use a TL1 single device interface, so it's very easy to do. And the second step will be actually using GMPLS. Now, if you look at the architecture, the user switch, when you have multiple exchange points like this in the world, that's probably what Glyph is trying to do. At some point, you're going to need to do more than just automating connectivity. You're really going to need networking functions so you can automate things and provide protection and stuff like that, and share the connectivity on demand. So you see how you can just justify, deploying a switch for just managing one node, and look at how it can be used later on when you're going to peer with the other sites. A more core network situation, Supercomputers a few years ago, they decided to go with photonic switching for purely economical reason. No other reason than that. They did a study, they look at dark fiber plus WDM plus photonic switching. So you remove SDH totally from the equation. They compared over 3 years to what it would take to deploy SDH cross-connects and lease SDH services, and at that time it was 90% cheaper, so they went with it. They also leveraged it to develop some new data grid application and did some very first experiments like VLBI among some sites that were having direct wavelength connectivity and not going through a router. But that was very experimental. There's a more recent network in Japan called JGen2. It's actually, I think, the most advanced network in the world in terms of control plane today. I'm not going to go into too much details. There's a person after me is going to talk about JGen2, and tomorrow Dr. Otani is going to present in the recent results session a lot more information about JGN2 and the control plane. So I encourage you to go and see it. Two things I want to mention is they did a recent and major interoperability trial. 2 carriers and 9 equipment vendors were involved. So it starts to be really interesting. It was a whole 9 yards: MPLS routers, GMPLS routers, SDS cross-connect, PXE and WDM. And they were able to deploy the full spectrum, the full hierarchy of what people call label switch paths, or those connectivity. They were able to connect wavelength connectivity, time multiplex connectivity, and MPLS. So that was a very good illustration of what control plane can do for you. The other thing they did, I think, was very smart for the Japanese organization, NICT, to divide the network into 2 subnetworks. It forced the 2 subnetworks to do interdomain. So they actually start to do some work on interdomain ENNI interface, and we work with some of them to provide an ENNI interface. So it's still in the first step. It's pretty static, but they can signal across multiple networks. To finish, I'm taking the Louisiana example. It's a state initiative to support high-end research, but the other component of it, which is very interesting, is also to foster economic development in that state. So they provide very cheap, very high-capacity connectivity, like 10 gigabit, and they're going to deploy that various places in the state, so it will create a business environment for universities to create startups and also having big companies invest in factories and development centers. What I like about the network is it's a very elegant network design where you have the multiple rings connected to a major hub in Baton Rouge, which is the other reason why I chose that network. It has a French flavor. And with just one switch, they're able to interconnect any site to any site. So they use another technology, RDM technology, to do connectivity within one ring, and they use a phonetic switch to provide that connectivity across multiple rings. And they can bypass routers in some cases to provide express connectivity. So, just one switch, if you build your network, can provide you a lot of flexibility. So with this, I'm going to conclude. So what's next? Right now, I talked about all optical switches, not all optical networks. I hope people notice the difference. So the next step is, could be all optical networks. The answer is yes, to my mind, definitely. But to some extent, there's going to be some islands of transparency for operation reasons and technology reasons. Photonic switching is not the only technology that you need to do that. That development is in pair with tunable transponders that are becoming available today, 2R and 3R regeneration technologies, and implementing control plane extensions to actually do spatial and also wavelength routing. Because when you do routing and wavelength assignment, it's a little bit more complicated than just doing spatial routing calculations. And you also need to do constraint-based routing. So that's the next step. The other aspect is faster networks. Monique talked about that as well. There's already a lot of demonstration on fast switches, micro and nanoseconds. But I think we'll take a lot more time to be integrated networks. There's a lot of work to understand. Now the bandwidth is almost for free, but computing space is more limited. How you can build networks with fewer or almost no buffer. That's a very different paradigm. So how you're going to use those technologies at that speed level is more than just the hardware. It's a really different paradigm. So I think that's going to take some time. Another way to do faster is just you can use that infrastructure to speed up the rate. So it's not faster switching, but you can have more capacity just by going from 10 gig to 40 gig, and that will happen. I think the last aspect is an increase in the better usage of the network resources. I think this is where the biggest and most interesting advances will happen in the midterm. For example, use of existing technologies and integrating the hardware, as I talked, the control plane, the middleware, everything, to provide some more advanced services. Today, if you want to connect different NRENs to provide some demonstration, like supercomputing is always a good example. It takes 2 months or 3 months of emails, and this should happen pretty soon in seconds, or I hope so. And that's, I think, the biggest value. Technology is good, but there's a lot of work to do to use them correctly. And hopefully, the application that you're developing will spur new ones in other areas, I hope. Thank you.
Okay, thanks Olivier for this inspiring idea. I'm glad that optical networks are perhaps closer to, near us, or in time at least, than I expected. Another thing I think was nice to know that we are not alone. I think there are other network providers who are working on this kind of things, and it's always good that there is more pressing needs perhaps by others, so that can help us also. Are there some questions from the floor? There is one. Can the microphone, where the hand is?
It may not be possible to do this in the time available to answer this question, but I'd really love to hear a brief review of the various technologies used to do photonic switching. Would it be true to say that photonic switching encompasses more than just MEMS devices? I want to know how the hardware works, basically.
Right. Can I, in very brief summary, I'm going to respond and then we can take it offline. Scalability is a limitation. So there's a lot of things in labs or limited environment, optical, using SOAs, for example, indium phosphide technologies. There's various technologies to do beam steering, MEMS or others, and there are other technologies to do that. The problem again is beyond 16 by 16, people don't know how to do anything because they are planar architecture. The advantage of 3D MEMS, which is the main technology deployed today for large cross-connect points, is that it scales with n, the number of inputs, and not n squared. And that allows to be scalable. So what's being deployed today, if you look at the application I've talked about, it's mostly 3D MEMS. Now in the future, people are going to have to solve scalability again, looking at potentially 3D architectures or finding some ways like SOAs to have signal amplification integrated with the design. So for example, for IP routers right now, people are looking at integrating hundreds of SOAs to do signal processing, amplification, switching on a wafer, to do multi-terabit all optical packet switches. But that's going to take probably 10 years before you see that in the network.
Okay, thank you very much. I think I would like to keep it. Oh, there's one question. Sorry. Short one then would be nice. Yeah, it's working, I think, or not?
Hopefully a shorter question. You mentioned facility-based networks as opposed to overlay,
right,
which I didn't understand the reference. Are those the things that we used to call mission-oriented networks? So, high-energy physics would have their own network. Is that the sort of thing you meant?
A little bit. It's much more an operational consideration. Overlay means you have equipment and you rent some connectivity, but you don't have to worry about it. And every 3 to 4 years, you're going to renegotiate a contract. It's really not you're not going to worry about it. You don't have a technical staff to worry about it. Versus some networks now invest in 15 to 30-year fiber IRUs, are deploying their own assets. And then it's a different mode of operation. They have to build a technical staff to maintain that network or subcontract. I think HEAnet and HEAnet 2 provides a very good example of that transition.
Okay, thank you.
Okay, thank you very much. Thank you again, Olivier. And Olivier made already a small bridge towards our next speaker, Masahiko Gino. He's from NTT, and he will talk about hundreds of wavelength switching even. So there's a lot to be switched over there, and he's also doing that in the GGN2 network in Japan. So it's really quite close to something that is in testing or production. The other thing I think what I really like in his presentation are the speeds I see. Normally I see always speeds of 10 gigabit or something like that. Yeah, that's what we use now, but I think we need speeds in 2 or 4 years, which are something like 100 gigabit perhaps. But at least I see in his resume something like 43 gigabit and the terabit LAN infrastructure. So I think that are steps we really have to go, because if 10 gigabit is now normal, at least for some people it's normal, I think we really have to look at speeds of not 40 but 100 and perhaps higher. So Gino, I hope that you are ready with all the logging in on your side, so that you can have your talk about the interesting subject on your side. I think we need to get... Let's see if we can handle it now. Okay.
Thank you. Good morning. I'm Masahiko Geno from NTT, and today I'd like to talk about advanced optical transmission and switching technology for next generation wavelength abundant IP optical networks. This is the outline of my talk. I'll begin with a brief introduction of rapidly growing broadband services and subsequent bandwidth explosion in core networks in Japan. Next, I'll describe hyperdense WDM technology that will support future high-capacity IP optical networks, such as generation of huge number of wavelengths and grouped wave switching and conversion. I will also present some experimental results obtained using JGN2 testbed. Finally, I'll show a terabit LAN architecture for application to grid computing as an example of grand use of wavelengths. This figure shows a rapid drop in monthly fees for NTT broadband services. The blue and red circles show the monthly fee for FTTH and ADSL, respectively, as a function of years. The number in the circle corresponds to the provided maximum bitrate for each service. The square indicates monthly fee provided by competitor companies. As we can see, by the appearance of the competitor companies, NTT was forced to drop the fee dramatically and had no choice but to keep the price low, even when NTT introduced fast access service to the market. As a result, 100 megabit per second FTTH service, in which 32 users shares a 1 gigabit per second access line, is now available in Japan at a monthly fee of about $40 US. This figure shows sustained growth in internet traffic at one of the major IX in Japan. The Japanese government estimates that internet traffic is 300 gigabits per second on average at present. As a result of keen competition, the number of broadband users in Japan is growing explosively, as we can see from this view graph. The number of ADSL users has reached more than 12 million. Even though the number of FTTH users is one order less than that of ADSL users at present, the growth rate of FTTH is somewhat higher. Last fall, NTT announced that in its middle and long-term management strategy that by 2010, it planned to shift 30 million customers to optical access and the next generation free IP-based networks. So the question is how to build an ultra-high capacity backbone networks to support the explosively growing IP traffic. In my presentation today, I will describe hyperdense WDM technologies as a key enabling technology. In order to achieve hyperdense WDM transmission, there are some issues that must be resolved. First, the precise control of the absolute optical frequencies of the optical channels and the WDM filter becomes increasingly important as the channel spacing narrows. Second, the crosstalk caused by forward mixing becomes more and more significant, even in the standard single-mode fiber. This view graph shows the configuration of a supercontinuum of multi-carrier light source that generate over 1,000 wavelengths within 6.25 gigahertz channel spacing. First, a 6.25 gigahertz, 6 picosecond optical seed pulse train is generated by using a 1567 nanometer C-level laser diode, a phase modulator, and a dispersive fiber. The seed pulse train is then amplified using an EDFA and coupled into a polarization maintaining dispersion decreasing fiber to super broaden its spectrum. The graph in the right hand shows the output spectrum. It exhibits spectrum broadening of more than 80 nanometers and offers 1,000 wavelengths optical carriers precisely spaced at 6.25 gigahertz. This figure shows the influence, the dependence of forward mixing crosstalk on the number of channels as a channel spacing of 6.25 gigahertz. As we can see, the forward mixing crosstalk increases with the number of channels, but sustained beyond several tens of channels. In order to hold the power penalty to less than 0.1 dB, the power channel optical power must be less than minus 11 dBm for a 1,000 channel transmission. This figure shows the filtering characteristics of an arrayed waveguide writing demultiplexer with a channel spacing of 6.25 GHz. In order to hold the power penalty to less than 0.1 dB, adjacent channel separation must be better than minus 18 dB. The employed demultiplexer can suppress adjacent channel by at least minus 21 dB and the far side channel by at least minus 38 dB. This figure shows a typical optical spectrum for hyperdense WGM signals. The wavelength ranges of the C band and the L band were 1539 to 1569 nanometers and 1572 to 1600 nanometers respectively. Both bands contains more than 500 channels. In order to confirm the feasibility of over 1,000 channel transmission, some experiments were performed using two field installed spans of 63 kilometer single mode fiber. The single mode fiber were part of the JGN2 testbed network. The JGN2 is an open testbed network environment for research and development and is operated by the National Institute of Information and Communication Technology of Japan. The lower graph shows the Q factor and corresponding to bit error rate for each channel after 126 kilometer transmission. As we can see, 1,046 channels were successfully received with a bit error rate of less than 10 to the minus 12. Next, in the hyperdense WGM network transporting over 1,000 wavelengths per fiber, we should employ the grouped wavelength path GWP concept, which groups wavelengths for the same destination and switches the grouped wavelength as one entity at an optical cross-connect OFC. By employing the concept, we can simplify the network management and reduce the size of optical matrix switch implemented in the OFC. A function to convert a wavelength group to another group is required to avoid any collisions in the OFC. In order to confirm the feasibility of grouped wavelength paths, some experiments were performed using JGN2 testbed. This view graph shows the configuration of grouped wavelength path OFC. This OFC consists of an 8x8 PLC-based matrix switch and a parametric wavelength converter. We use quasi phase-matched lithium niobate waveguide, QPM NREN, as nonlinear media for parametric conversion. In order to achieve polarization-independent operation, we used 2 QPM NREN in the polarization diversity configuration. This is the experimental configuration. Two streams of grouped wavelength paths that consist of 64 wavelength channels each were generated by a supercontinuum light source. Let's suppose the two streams of grouped wavelength paths are from different sources but in the same waveband, and they are switched to the same output fiber port for the same destination. In order to avoid a collision between the two grouped wavelength paths in the same waveband, we must convert one of the grouped wavelength paths to another waveband. This shows the spectra of the input grouped wavelength paths and converted wavelength path. The transmitted signal quality evaluation results are shown in these figures. This figure shows the output spectrum of the switched and waveband converted group wavelength path after 32 kilometer single mode fiber transmission. Uniform waveband conversion was achieved in the field environment. We measured the Q factor and we confirmed a bit rate of less than 10 to the minus 9 for all the channels in the grouped wavelength path. These successful results are encouraging and indicate that the grouped wavelength path concept is feasible in a practical environment. As the last topic of my talk today, I will introduce the Travitan architecture concept for the application of grid computing among supercomputers, which represent a grand use of wavelengths. The Travitan architecture is the first circuit switch network connecting supercomputers and servers. It transports massive amount of data through parallel WDM interfaces. A wavelength group is assigned for wavelength bank according to the delay requirement of the applications. The bit phase of each wavelength is adjusted on the receiver side. The wavelengths are released as soon as data are transferred. The Travitan architecture is for supercomputers, especially with grid applications. In such applications, CPU resources are shared through high-speed optical networks, and real-time visualization of output from multi-CPU calculation is required. The most important point to note is that in such applications, the low latency makes grid computers more powerful. This view graph shows how low latency is so important using a computing grid example. In the computing grid, computing resources are distributed and connected to each other through an optical network. Since a massive amount of data are transmitted between computers like this, calculations will take a long time. So the delay should be as short as possible. And the delay consists of the propagation delay, but it's no help. And the queuing delay, transmission delay, and access delay. Our proposal to decrease this delay is to introduce parallel transmission through the grand use of wavelengths. For single wavelength use, a data set is divided into an arbitrary number of blocks and transmit in a serial manner, taking a long time. On the other hand, for multi-wavelength use, each block is transmitted in a parallel manner across parallel WDM interfaces, signals. It should be noted that the delay decreases as the number of wavelengths increases. Virtual concatenation, this queuing, helps the data sequence integrity. fast optical channel provisioning using the control plane also help. By using this view graph, I will show how the Teravitran works. The Teravitran consists of a lambda source and a fast optical switch and a parallel optical interface with virtual concatenation. The lambda source, a supercontinuum, for example, provide a highly accurate optical frequencies to parallel optical interface. When this supercomputer needs a delay critical data transmission to the visualizing server, it requires and resolves the 6 wavelengths via control plane and the 6 set of rocks are transmitted using 6 parallel WGM signals. When the transmission is completed, the 6 wavelength resources are released. For the delay non-critical application, 2 wavelengths are used, for example. The wavelength group is assigned and released dynamically, and the performance is and now performance estimation based on block probability is now being tested with and without waveband conversion. Now I'd like to summarize my presentation. A rapidly growing broadband service and the subsequent bandwidth explosion in quantum network require more and more wavelength resources. I presented hyperdense WGM technology, such as the generation of a huge number of wavelengths and group wave switching and conversion. I also presented some experimental results obtained using the JGN2 testbed that confirms the feasibility of the hyperdense WGM concept. I presented the Teravitran architecture for grid computing application as an example of ground use of wavelengths. Thank you for your attention.
Okay, that's interesting. I think perhaps it's far away, but I think it's very interesting certainly to see the parallel usage of wavelengths like in a computer, 8 bits, 64 bits, what do we have? So it is a possibility of solving the issues, but I wonder how much implications it will have in making this kind of networks. Will it be simple to upgrade our present, what you call single bit networks, let's say an 8 parallel bit network? Would that be easy, or what are your ideas about that?
About Teravitran architecture?
Yeah.
And your question is for a 6 wavelength parallel transmission is easy to implement to a concrete system?
Indeed, yeah. Because the delay variation and all the other technology issues related to that.
Yes, right. And now this architecture is a stage of creating a concept, and we need more discussion, especially with great people. And there are many issues to be solved. One is the skewing. And so the skewing means for example, 10 wavelength signals are transmitted, and there are dispersion in the fiber, so the time they reach to the destination is different for the wavelength. So we should achieve method to describe, maybe in an optical domain and an electrical domain, both domain. We have to develop such technologies.
It's very interesting. I hope that somebody in this audience really wants to test it out and get it at a large scale, because I think it's the next phase. Are there more questions about the subject? No, sorry, can you wait for the microphone? Over there, on the corner here. There.
I understand there is some optical reach limitation of such technology, since it's based on optical noise generation, and that you're using that for local and small networks. But I would be interested to know, what is the reach limitation? Is it tens of kilometers? Could it be potentially later hundreds of kilometers if there were some amplifications, or thousands?
You're asking about the 1000 data transmission or Chebyshev architecture?
I'm asking, what is the limitation in distance of propagation?
In the terabit line, so this is the parallel one.
Right.
Yeah. So
I think in the case of Chebyshev architecture, there is not so strict limitation of propagating distance, because the bitrate is not so high, maybe 10 gigabit per second or so. The concept is to virtually concatenate the many wavelengths, and we can transmit the huge amount of data, like 100 gigabit or gigabit per second, directly at the same time. So the bit rate is not so high. So I think the restriction of propagation distance is not so high.
I have a question. At the end of the presentation, you suggested that in order to improve performance when you want to transfer data in a grid computing environment, you may have multiple lambdas working in parallel. And my question was, well, did you consider the fact that typically when you want to transfer data, you have a bottleneck which is not the network, but rather the read and write performance that you typically experience when you write to the disk? So even if you add more lambdas, it may turn out that you're not able to increase the performance because the bottleneck is the disk. Did you consider that in your proposal?
Yeah, I don't understand exactly your question. And,
okay, you can take it offline, maybe.
Yeah, I think the issue is that the read-write on a disk is slower than the bandwidth you promised to give. So.
Okay, so you mentioned about the bottleneck is not transmission, and maybe in the other side, or maybe on the server side or so.
Yeah.
Maybe, yeah, you're right. And we have to resolve such a bottleneck one by one. And my concept is one of such technology to resolve such issues.
Okay, thanks.
Thank you.
Okay. Thanks again. I think it was a good overview of the technologies, getting from GMPLS to parallel wavelengths. I think that's a good view of where we are with optical networking. I want to thank you again for being here, and also the other presenters. I think lunch is being served at the usual place, at the usual time. So thank you very much.